The name of this module is UMPU test for multiparameter exponential family 3. In the last lecture, we derive UMPU test for a k-parameter exponential family in case of one-sided alternative, that is for h naught theta 1 less than equal to theta 1 naught versus h1 theta 1 greater than theta 1 naught. In the present lecture, we considered the UMPU test for the two-sided alternative h naught theta 1 equal to theta 1 naught versus h1 theta 1 not equals to theta 1 naught. As in the previous case, first we shall derive the conditional UMP test given t upper 2, and then we convert this test to the unconditional UMPU test of level alpha. We make use of ancillary statistic to simplify the test procedure. Some examples are discussed in this connection. In the last module, we have discussed the construction of UMPU test for h colon theta 1 less than equal to theta 1 naught versus h a colon theta 1 greater than theta 1 naught. In the present module, we considered the UMPU test for testing h naught colon theta 1 equal to theta 1 naught versus h1 theta 1 not equals to theta 1 naught. That is, here we consider a two-sided problem. As in the previous case, we define g theta t is of the form c theta into e to the power summation ti theta I ti into ht. So t1 given t upper 2 follows one parameter exponential family with parameter theta 1. The test function is given by psi naught t is equals to 1 if t1 less than some c1 or t1 greater than some c2. Here c1 and c2 are functions of t upper 2, equal to gamma I t2. Gamma is a function of t upper 2 if t1 equal to ci for I equal to 1 comma 2, equal to 0 if t1 lies between c1 and c2, where c1, c2, gamma 1, gamma 2 are such that expectation of phi naught under theta 1 naught given t2 is equal to alpha, and expectation under theta 1 naught t1 into phi naught given t2 is equals to alpha into expectation under theta 1 naught t1 given t upper 2. Actually, we derived these conditions earlier in case of one parameter exponential family. Phi naught is conditionally UMP given t2 in the class Cu alpha theta 1 naught. This is the set of all phi such that the conditions 1 and 2 as previously stated are satisfied. To show that phi naught is UMPU unconditionally at level alpha, let phi be any unbiased test for testing h naught colon theta 1 equals to theta 1 naught versus h1 colon theta 1 not equals to theta 1 naught. Phi is unbiased imply phi is alpha similar on script theta b. It follows from our result 1 in previous lecture. This implies phi has a Neyman structure with respect to t upper 2 over script theta b. It follows from our result 3. This implies expectation of phi given t upper 2 is equals to alpha almost everywhere. Since phi is unbiased, that is expectation of phi under theta has a minimum at theta equal to theta naught, and therefore from the first order condition we have the derivative of expectation of phi and with respect to theta 1 naught is equals to 0. Now expectation of phi is equals to integral phi c theta exponential theta 1 t1 plus summation over I from 2 to k theta I ti h t dt, and differentiating with respect to theta 1 naught we get expectation of theta 1 expectation of t1 theta plus the derivative d c theta by d delta theta 1 naught by c into expectation of psi, and equating it to 0 we get expectation of t1 into theta minus expectation of t1 into expectation of psi is equals to 0, and therefore derivative of expectation of psi with respect to theta 1 naught is equals to 0. After some mathematical derivation, actually we finally get expectation of t1 psi given t upper 2 is equals to alpha into expectation of t1 given t upper 2. We write this as equation 4 here. Hence phi belongs to cu alpha comma theta 1 naught. So expectation of phi naught given t upper 2 is greater than equals to expectation of phi given t upper 2 for all t upper 2 and for all theta such that theta 1 not equal to theta 1 naught, or expectation of phi naught is greater than equals to expectation of phi for all theta such that theta 1 not equals to theta 1 naught. But phi is any unbiased level alpha test. Hence phi is unconditionally UMPU at level alpha for testing h naught colon theta 1 equals to theta 1 naught versus h1 colon theta 1 not equals to theta 1 naught. Now we find a statistic v. V is a function of t1 and t upper 2 such that v and t upper 2 are identical IID under script theta b, and v is a linear function of t1, that is v is of the form a t upper 2 plus t1 into b of t upper 2 for each fixed t upper 2 and b t2 greater, and this is greater than 0. Therefore expectation of t1 psi naught given t upper 2 equals to alpha expectation of t1 given t upper 2 imply expectation v minus a divided by b into psi naught given t upper 2 is equals to alpha into expectation of v minus a divided by b given t upper 2, and this is equivalent to expectation of v into psi naught given t upper 2 is equals to alpha into expectation of v given t upper 2. Therefore t1 less than c1 is equivalent to v less than some c1 star, and t1 greater than some c2 is equivalent to v greater than some c2 star. Hence the alternative UMPU test is given as phi naught v equal to 1 if v less than c1 or v greater than c2, equal to some gamma I if v equal to ci, I equal to 1 comma 2. Here we make use of randomization, equal to 0 if c1 less than v less than c2, where c1, c2, gamma 1, gamma 2 are such that expectation of phi naught is equals to alpha, this is our size condition, and expectation of v phi naught is equals to alpha into expectation of v. Actually it comes from the unbiasedness condition. The choice of v is ancillary for script theta b, and v is a linear function of t1. If further v is symmetric about some constant a under script theta b, then the UMPU test can be given by phi naught v equal to 1 if modulus of v minus a greater than some c equal to gamma, if v minus a equal to c equal to 0, if v minus a less than c, where expectation of phi naught is equals to alpha. Now we consider some examples. In our first example, we draw a random sample of size n x1, x2, xn from normal mu sigma square population. We are interested in testing h naught sigma equal to sigma naught against h1 sigma not equal to sigma naught, and number 2 h naught mu equal to mu naught versus mu not equals to mu naught. First we consider the solution of 1. The joint PDF of x1, x2, xn is given by p theta x. Let us choose theta 1 equal to minus 1 by 2 sigma square, t1 equal to summation xi square, theta 2 equal to mu by sigma square, t upper 2 equal to nx bar. Then we define v equal to t1 minus t upper 2 whole square by n, where a upper t2 equal to minus t2 square by n and b t2 equal to 1. Therefore, v is a linear function of t1 for fixed t2, and of course v and t upper 2 are independent. It follows from the fact that summation xi minus x bar square is independently distributed of x bar. Then the UMPU test is given by phi naught v equal to 1 if v by sigma naught square less than c1, or if v by sigma naught square greater than c2, equal to 0 if c1 less than v by sigma naught square less than c2, where c1 c2 are such that expectation of phi naught is equals to alpha under sigma naught square, and expectation of v into phi naught is equals to alpha into expectation of v. And simplifying these conditions, we get, after some mathematical derivations, probability c1 by sigma naught square less than chi square n minus 1 less than c2 by sigma naught square equal to 1 minus alpha. And from the second condition, that is from the condition expectation of v into phi naught equal to alpha into expectation of v, we get probability c1 by sigma naught square less than chi square n plus 1 less than c2 by sigma naught square equal to 1 minus alpha. Actually, we have also derived these conditions in a previous module in case of one parameter exponential family. Now we consider the solution of the problem 2. Here we redefine theta 1 as mu by sigma square, t1 equals to nx bar, and theta 2 equals to minus 1 by 2 sigma square, t upper 2 equal to summation xi square. Now here we define v. V is equals to t1 by root n divided by t upper 2 by t1 square by n divided by n minus 1, and it is ancillary for script theta b, that is the set of all theta with mu equal to 0. Define w equal to t1 by root n divided by root over of t upper 2, and it is ancillary for script theta b since it is independent of sigma and linear in t1, and w is symmetric about 0. The UMPU test is given by phi naught w equal to 1 if mod w greater than c, equal to 0 if mod w less than c, where expectation of phi naught under mu naught is equals to alpha. Now we consider our second example. Here we draw a random sample x1 y1 up to xn yn. It's a paired sample from a bivariate normal population with 5 parameters mu1, mu2, sigma 1 squared, sigma 2 squared, rho. We are interested in finding an UMPU test for h naught rho less than equals to 0 against h1 rho greater than 0, and number 2 h naught rho equal to 0 versus h1 rho not equals to 0. Now we consider a solution of this problem. Let theta curl, theta actually a vector with 5 parameters, and script theta b equal to set of all theta with rho equal to 0. The joint density of x curl and y curl is given in this form. It is a form of bivariate normal distribution. Now we define theta 1. Theta 1 equal to rho by sigma 1 sigma 2 1 minus rho square. T1 equal to summation over I from 1 to n xi yi. Also t upper 2, here we define t upper 2 is a vector valued statistic with 4 elements summation xi square. summation yi square x bar y bar. So accordingly we can define v equal to summation xi minus x bar into yi minus y bar divided by within root over summation xi minus x bar square into summation yi minus y bar square. This is equals to t1 minus some g1 is a function of t upper 2 divided by g2 t upper 2, and it is increasing in t1 and it is linear in t1 for fixed t2. Hence UMPU test for h0 rho less than equal to 0 versus h1 rho greater than 0 is given by phi naught equals to 1 if root n minus 2 into v divided by root over 1 minus v square is greater than t alpha n minus 2, and 0 if root over n minus 2 into v by root over 1 minus v square less than t alpha n minus 2, where t alpha n minus 2 is the upper alpha percent 100 into alpha percent point of a t distribution with n minus 2 degrees of freedom, and actually here v represents the sample correlation coefficient, and the UMPU test for h0 rho equal to 0 against rho not equals to 0 is given by phi naught is equals to 1 if root over n minus 2 into mod v by root over 1 minus v square greater than t alpha by 2 comma n minus 2 equal to 0 if root over n minus 2 into mod v divided by root over 1 minus v square less than t alpha by 2 n minus 2. It is a two-sided test, and as in the previous case, t alpha by 2 n minus 2 is the upper 100 into alpha by 2% point of a t distribution with n minus 2 degrees of freedom. In this lecture we see that how one can derive UMPU test by using the conditional UMP test. Here we actually considered three examples. In the first example, we considered the test for sigma equal to sigma naught versus sigma not equal to sigma naught in normal mu sigma square population where mu is unknown. We see that here the test is a two-sided test based on the statistic summation xi minus x bar square by sigma naught square under h naught which follows chi-square distribution. In case of test for mu, normal population mu equals to 0 versus mu not equals to 0, we derive the test and we see that it is a two-sided test based on the statistic root n x bar by s which follows t distribution under h naught. In our third example, we consider a test for rho equal to 0 versus rho greater than 0 and also for rho not equals to 0 in case of bivariate normal population. We see that this test is based on the statistic root n minus 2 into r divided by root over 1 minus r square, and actually here r is the sample correlation coefficient between x and y, and here under h naught the null distribution is t distribution with n minus 2 degrees of freedom.